Welcome back to our series of lectures on the topic electromagnetic spectrum, absorption spectra. In this concluding part today, we will continue our discussion on IR spectroscopy and we will particularly be talking about interpretation of IR spectra. The session is planned as follows, that is, to begin with, we will briefly recall what we did in the previous session. Thereafter, we will formulate a strategy for the interpretation of IR spectra. Having done that, we will come to the main theme of today's session, that is interpretation of IR spectra. For this, we will take up a number of examples. We will take spectra of different molecules there, and on the basis of spectra, we will try to decipher or try to work out what is the functional group of the molecules to which the spectra belong. Then towards the end, we will try to sum up what we do in today's session. Okay, let's briefly recall what we did in the previous session. In the previous session, we did two main things there. Firstly, we discussed structure spectral correlations. That is, what we did was we took the spectra of a large number of known molecules. That means we knew the molecular structure, we had a spectra for that. Then we tried to find what are the kind of correlations between the spectra and the structure of molecule. We took a number of examples for that, which were spread over a wide range of functional groups. Thereafter, we compiled all this, because in each case we identified the characteristic vibration frequencies and then we compiled them together, so that we can have a ready table with us to look into that in terms of the interpretation of IR spectrum. Okay, let's move further and look at the strategy for interpretation of IR spectra. If you really ask me, there is no unique way of interpreting an IR spectra. Everybody has one's own way of trying to look at a spectra and try to get information from there. And typically, with experience, you can devise a strategy of your own also as you proceed further. Now, one of the ways of doing, which I am going to share with you, essentially starts by making a statement that the prime focus when trying to look at IR spectra is in the characteristic group frequencies region, that is from 1500 centimeter inverse to about 4000 centimeter inverse. The region below this, say from about 650 to about 1500, that is the region for fingerprint region there, which is used to some extent, but not in isolation, but in kind of in combination with the group frequencies region there. We will see that, because if possible, try to revisit what we did in the previous session. If you can have a look at the previous session, that will be really helpful to make use of while trying to interpret IR spectra. Okay. Now, anyway, how do we go about it is that if you have a spectrum with you, you draw a line around 3000 centimeter inverse. That is one starting point, one way of doing it. And when we do that, and if you look around there, the typical patterns what we come across, that is, we can have signals which are immediately below this value of 3000 centimeter inverse. They belong to the aliphatic CH stretching there. That is one of the most common signals, because most of the molecules will have something of in this region over there. Then similarly, if I look towards the higher side of it, that means slightly above 3000 centimeter inverse, I find if there are some signals there, they may belong to the aromatic CH stretching or unsaturation there, or maybe that will be in the order of, suppose you have got this is 3000 centimeter inverse and I am trying to go upwards there. So, something very close to this, say about 30 centimeter inverse, that is typical for aromatic CH there. Then if I go slightly beyond that, about 3100 or so, or slightly more than that, that could be a double bond, C double bond C. Or if I go further, about 3300 or so, this will be C triple bond C. So, that is how it comes. So, typically the region close to about 3000 centimeter inverse is very, very rich in terms of information there. Okay. Now, when we move further, we continue looking around there. If you have got some broad signal somewhere in the range of 3300 to 3500 centimeter inverse, they are suggestive of hydrogen bonded OH or NH. Suppose that is a broad signal, the typical, because if there is an OH or NH there which have a sharp signal, that indicates that these groups are free there. But if, and typically they are into some kind of hydrogen bonding, in such cases we get broad spectra. We have seen the spectra in the previous session. Now, as I just mentioned, if the signals are sharp, it could be OH or NH or even NH2. Now, if we have got another typical thing to look forward to in this region of the spectrum is, that is, if you have got a pair of signals around 2700 to 2900 centimeter inverse, there are two lines over there, and these along with a signal for a carbonyl stretching around 1700 centimeter inverse, they suggest aldehyde group. This is a kind of a short thing. That means you have a signal, two signals there in this range, and along with that we have a signal around 1700 centimeter inverse, slightly above or below this. So these two put together, they are typical indicators of an aldehyde functional group in the molecule. And if you have got an OH signal, which is a broad signal but you observed around 3300 centimeter inverse or so, if it is accompanied with some kind of a shoulder around 2500 centimeter inverse, that is indicative of a carboxylic acid there. So this all we have done in the previous session. I am just trying to put them together for you so that we can refer to this and move further in trying to interpret IR spectra. Let us go a little further. Now, in addition to the region around 3000 centimeter inverse, having done that, then we move on to the characteristic vibration frequencies in the range from 1500 to about 2500 centimeter inverse. When we look into this, what to look forward to? One typical thing which we have to look forward to is a sharp signal in the range somewhere around 1650 to 1800 centimeter inverse. More often than not, it is around 1700 centimeter inverse. That is typical of a carbonyl group. And this is a very common observation because there are a number of functional groups which are based on a carbonyl functionality over there. Now, then once you get a signal in this range here around 1700 centimeter inverse, then we can explore for other related signals to get the functional group there. For example, you have got a carbonyl group there, look for a shoulder around 2500 centimeter inverse, the two put together will indicate a carboxylic acid group there. Or a carbonyl group here accompanied with say two signals around 2700 to 2900 centimeter inverse, which are typical of aldehyde, the two put together will make this carbonyl group to be an aldehyde. So that is what we mean by exploring other possibilities there. Okay. Now, in addition to this, the same region has another very significant signals there. That is, we have medium intensity signals around 2200 centimeter inverse. This again is very significant here. Any signal in this range, which is of a not a very intense signal, but a medium range signal, that is indicative of either a C triple bond C or a C triple bond N. That means basically either you have got a alkyne or a nitrile kind of a molecule there. So this again is a very significant observation because this itself accompanied with some other observations there will be very helpful in deciding what is the functional group of the molecule there. And yet another thing is that this again is very characteristic of an ether, that is a sharp signal around 1050 to 1150 centimeter inverse is indicative of an ether. This is characteristic there because this ether basically is the signal here is for COC. COC stretching is very typical at this range over there. So this is a very important signal to look forward to in terms of interpretation of IR spectra. Okay. Yet another thing which probably will be very useful here is that if I want to confirm whether the molecule is aromatic or not, there are two things one has to look forward to, rather three things to be more specific. One is a signal around 30 centimeter inverse, which basically is aromatic CH there. That's one stretching vibration there. Then in addition to that, we have got one signal somewhere around 1500 to 600 centimeter inverse. This is for aromatic C double bond C we talked about earlier. Then if these two are there, they are indicative of some kind of an aromatic moiety there. But in addition to that, if we have kind of medium range or even intense signals in this range there, maybe two signals there or three signals there. So these put together, this basically are meant for indicating the substitution pattern on the aromatic ring there. So these three put together are very important signals for the molecules which are aromatic in nature. Okay. So we have just basically what we have done is we have seen that if I want to interpret an IR spectrum, what do? I start by looking at the region around 3000 centimeter inverse, slightly below or slightly above it, and then having done that, look for the characteristic signals there. Thereafter, we focus attention on to the region from 1500 to 2500 centimeter inverse, and there are certain characteristic frequencies to look forward. So, and then all this put together will be used to work out the functional group of a given molecule. Now we come to the main theme of today's session, that is interpreting IR spectra. We will take number of examples here. So now what I am going to do is I will take up certain spectra for which I do not know the molecule. Just on the basis of spectra, I will try to use this information which I just shared with you and try to see what is the functional group of the given molecule. Let us take the first example. Now the spectra here it needs to be interpreted. And as I just mentioned before, basically in order to work out the functional group of the molecule, we focus attention on the characteristic group frequency region, that is somewhere around 1500 centimeter inverse to 4000 centimeter inverse. And this region happens to be a fingerprint region, which we will be touching upon only once in a while. Okay. Now, in order to move further, what do I do is I start by drawing a line around 3000 centimeter inverse and then look for the signals slightly in the neighborhood of this place. So, what do I find? That for this particular spectrum here, these signals here, they are typical of the CH stretching there. But what I am tempted to go further to is that in this molecule, I am having a very, very intense signal somewhere here. This is around 1700 centimeter inverse. This is such a typical signal which cannot be missed as such, is for a carbonyl group. So, this made me tempt to look into this signal prior to even this region over there, because this is a very, very significant signal there. Then what do I do next is, if I look into this, I find that in this region here, when I had CH stretching here, I am having two signals here. These two signals actually are very, very typical of an aldehyde CH, that is the CH of the aldehyde functional group, that is CHO. So, these two put together give me the answer. I do not have to look for anything further than this, because these two put together tell me that I have a molecule which is aldehyde in nature. But there is one signal here which is slightly kind of distracting here, because this we cannot really interpret here. This apparently happens to be some kind of an overtone of this signal there, because the vibration frequency here is roughly double that of this frequency there. So, this happens to be an overtone and not a signal which has to be considered over there. So, we can conclude that for this molecule here, the functional group happens to be aldehyde. I have just jumped on a few things because I have taken an example which is very, very straightforward, because in this case the carbonyl group and the associated CH of aldehyde is straightforward there. So, we can straight away come to the conclusion that it is an aldehyde. Okay, let us move further. Take second example. Now, in this case, what do I see? Again, my strategy is the same. I draw a line around 3000 centimeter inverse and look around. What do I find? I find that in this region here, there is a medium signal around 3300 centimeter inverse, which again is very, very typical, because this is characteristic of either OH or NH group there. And in addition to that, we have a signal around 3070 centimeter inverse, and that is typical of double bond C H stretching. That means it is an alkene kind of a situation, unsaturation is involved in that. And of course, these signals are typical CH stretching and all. Then there is one more prominent signal somewhere around here, that is around 1640 centimeter inverse. This basically is our C double bond C stretching there. Now, with these things, if I just try to look at the possible functionality here, this will be an unsaturated secondary amine there. Why unsaturated and why secondary amine? Let us try to look back again. Unsaturated because I have got two indications here, one around 3070 accompanied with this signal here, which basically is my C double bond C stretching there. So, these two put together will give me an indication that I am having a unsaturation in the molecule, and this signal here could be an OH or an NH, but since it happens to be, this is a possibility that it happens to be an OH group or an NH. If it is an NH, it cannot be a primary amine, it has to be a secondary amine. You remember that for a primary amine we will get two doublet over there, for secondary amine we get a singlet here or a single peak over there, and for tertiary amine we do not get this signal at all. So, this is a likely functional group for this molecule is unsaturated secondary amine. Okay, let us move further. Let us move further and look at this molecule. Now, this molecule has got slightly very, very broad spectra in this region. Let us see what sense we can make out of it. Again, we start by drawing a line at 3000 centimeter inverse and look around here. We find that there is a broad signal there, a very, very broad signal starting from about 2500 centimeter inverse to 3500 centimeter, a very, very broad signal there, which is an obvious thing that it is happens to be an OH or NH, more likely to be an OH signal which is hydrogen bonded there. It's a broad signal, is very, very straightforward there. In addition to that, what we find is that this signal is again very tempting to look at, because anything around 1700 centimeter inverse is very characteristic of a carbonyl group. So, we cannot miss it ever. So we have an intense signal around 1700 centimeter inverse, which tells me there is a carbonyl group in this. Now, if we move further and make one very interesting and important observation here, this is very typical here, we mentioned before also, that is, a shoulder around 2500 centimeter inverse is indicative of a COOH now. That means, if we have a broad signal here and accompanied with a shoulder around 2500 centimeter inverse, that tells me that this is a carboxylic group, and this is not NH, it happens to be an OH over there. So, this is a carbonyl, and then OH put together, the two put together will add to give me what is called as a carboxylic functional group. So, this molecule this is a spectrum of a carboxylic acid functionality over there. But what kind of a carboxylic acid is this? Is it an aliphatic one or an aromatic one? We find that there is no indication of an aromatic ring. For aromatic ring to be there, what we expected was there should have been some signal around 30 centimeter inverse. Maybe it is superimposed by this broad signal there, that is a possibility. But if it was an aromatic one, we must also have something around 1600 centimeter inverse, which we do not have. Going further, if it was an aromatic molecule, then probably would have expected something in this region also, which tells about a substitution pattern of that. This again is missing. So, we can conclude that this molecule is not aromatic in nature, it is an aliphatic carboxylic acid. So, we see that just by looking at a few things in the spectrum, we can make a reasonable conclusion about the nature of the molecule. Let us move further. Look at this molecule. Now, again we draw a line at 3000 centimeter inverse and look around. Obvious thing, the straightforward thing what we look forward to is, this is a broad signal over here spreading from about 3100 to 3500 centimeter inverse, which typically could be an OH or NH there. Okay. Then what you find is, if I look at this region here just below 3000 centimeter inverse, we got CH stretching, which is indicative of aliphatic CH stretching there. Then what you find is that this whole region is blank, there is nothing significant over here, and we have only signal which is somewhat significant, that is around 1450 centimeter inverse, which is typical of CH bending. So, what does it mean? Again, in this case also there is no indication of an aromatic ring over there, because 3030 is missing and so is 1600, and there is nothing in this region as well for the substitution. So, aromatic is not there. Again, we are dealing with a molecule which is aliphatic in nature, and the possibility could be an aliphatic alcohol, there is nothing else. It could be an amine also, but if it was an amine, probably would have expected a primary amine having a two signal over there rather than one signal there. And in case of amines, we also expect something in this region which is not CH bending, but that is for the NH bending and all. So, we conclude that this molecule is likely to have to be an aliphatic alcohol, because mind you that IR spectrum does not give you a conclusive evidence about the nature of molecule, it is suggestive there. So, we have to supplement it with the information from other spectroscopies like UV or NMR, about which you will be learning in the third year of your studies there. So, all spectroscopies put together are made use of in trying to work out the structure of the molecule. But all said and done, IR spectrum does give you a reasonably good indication about the nature of the functional group in the molecule, because once you are dealing with the molecule, we also know the history of the molecule. How has the molecule been made? What is the molecular formula for that, or rather the molecular weight? So, all put together, all these informations can be synthesized to work out the likelihood of the nature of molecule. Okay. Let us move further and take another example here. Again, our objective is the same, that is, we need to identify the functional group to which the molecule whose spectrum I am going to show over here belongs there. Okay. Now, I am just skipped that line over there at 3000 centimeter inverse, because it was so tempting to look at that there are two signals here, 3180 and 3350. This is very strong indication that I am dealing with something like NH2, which could be an amine or an amide. Both are the possibilities, because in both the cases we get signal of this kind. Then what you find is that this region here is CH stretching, which is typical. By now we know it very well that this is a typical thing to look forward to, that this basically is an aliphatic part of the molecule. Then another tempting thing to look at is a signal at 1640, which is likely to be a carbonyl stretching, CO stretching, because that extends from about 16 to 1800 centimeter inverse, roughly around 1700 is more often than not. Now, with this put together, we can just say, because this carbonyl and an amino group there, these two put together are good enough indication to suggest that this molecule happens to be a primary amide, okay, because this NH2 and there's this carbonyl there. Again, one more thing which we have been observing in the previous spectra also, that this molecule also happens to be aliphatic in nature. It's just incidental that all this molecule happen to be aliphatic, because there is no signal around 3030 for aromatic, or 1600 or somewhere in this region there, where we have to look forward to the substitution pattern there. So, this again is an aliphatic primary amide. So, that is the nature of the molecule to which the molecule for the spectrum belongs. Now, let us move further and look at this molecule. In this molecule, one obvious signal which is there is somewhere here, which belongs to the CH stretching, the aliphatic one here. And the most significant observation in this case happens to be this signal here around 1640 centimeter inverse, which is typical of a carbonyl stretching there. And in addition to that, what you find is that if this is carbonyl, one possibility could be it could be an aldehyde or a ketone. But if I want to look for an aldehyde, we have to look for two signals around 27 to 2900 centimeter inverse, which are missing here. So, this is not an aldehyde there. So, this is basically some kind of a ketone over there. It's not an aldehyde, it's a ketone. Okay. Again, we do not have any signal above 3000 centimeter inverse. What it means is that it is not aromatic, because aromatic must have a signal around 3030, and unsaturation has to have signals beyond that. So, there is no unsaturation, there is no aromaticity here, and even the signal at 1600 centimeter inverse, which is typical what we look forward to in case of aromatic molecule, again is missing. So, this molecule happens to be again aliphatic in nature, and this, as happened in one of the cases before also, this small signal here is an overtone of this carbonyl stretching there. So, this is roughly at double the frequency of this one. Typically, carbonyl groups gives overtones in the IR spectra there. So, what we conclude? We conclude that the likely functional group for this molecule is simple ketone, because this is a good enough indication in the absence of any other combining thing, because there is no shoulder around 2500. So, it cannot be carboxyl group there, there is no OH here. So, this carbonyl group is just for a simple ketonic molecule there. Okay. Let us move on to the next example here. Again, objective is to identify the functional group. So, what you find, the significant peaks in this is obvious one here, which is basically CH stretching. And then what we have is, this is one thing very, very significant. We haven't come across this signal so far in all these examples here. This is at around 2250 centimeter inverse, which we know from our that compilation of the data of the known molecules there. We know that this is either C triple bond N or C triple bond C. I mean, either it's a nitrile or it is a alkyne group. Okay. Let's move further. Let's try to see which of the two happens to be, because this is again very, very characteristic. So, our functional group has to be either this or this, nothing else, but we have to work out which one of the two. We go further and we find that there is no signal beyond 3000 centimeter inverse. That means it is neither aromatic nor unsaturated one, because there is no C double bond C or C triple bond C there. And then let us move further and we find that there is no signal around 3300, because this 3300 signal is very, very characteristic of this CH, C triple bond C H there. So, had it been this functionality, then if it was an alkyne, probably we would have expected that this signal is there, which is not. So, we can say that this molecule is not alkyne, but it happens to be a nitrile having a functional group as C triple bond N there. So, we conclude that this molecule happens to be a nitrile there. And just to augment that, we have a signal around 1450, which basically is CH bending, that is typical of aliphatic moiety over there. So, this signal is not very significant, but in supplementation with this indicates the hydrocarbon part of it, that is all. Okay. So, our conclusion stands that this molecule happens to be a nitrile. Okay. let's move further. Look at yet another example here. Now, this molecule is very different here. Let's see. Now, again, the most prominent signal here is somewhere around 1685, which we know that by now that this happens to be a carbonyl group, and since it happens to be around 1685, it is on a lower side. This indicates that this could be a carbonyl group which has been conjugated, because by conjugation the lambda that this vibration frequency decreases a little. Okay, let's move further and look at what is this here. We find that there is a signal slightly close to about 3000 centimeter inverse, slightly on higher side. It is a very weak signal, not as normally what we expect for a aromatic compound, that we do get a signal which is indicative of an aromatic CH there. But if it is an aromatic one, we have to look for one more signal, and that is right here. That is around 1600 centimeter inverse. This is again the signal because of the aromatic ring there, because this signal on its own does not indicate that it is going to be aromatic, likely to be aromatic, fine, but not exclusively it is an aromatic molecule, because for an aromatic to be there we had to have more information, and that information is coming from a signal somewhere around 1600 centimeter inverse, and further down we have got more information here. That is, this is typical of a mono substitution. That means an aromatic ring which has got a single substituent on that, that will give you this characteristic pattern in this region over there. So, 1, 2, 3 pieces of information put together conclusively tell me that this molecule happens to be aromatic, and also this the first signal we spotted here of a carbonyl group. So, that means this molecule is an aromatic, and of course, it has a carbonyl group with that. But if I want to see what is the nature of this carbonyl group, maybe I can look for something somewhere here, say around 2700 to 2900. I find that the doublet over there, which is typical of an aldehyde, is missing. So, that is not there. That means this molecule must be a ketone there, because we do not have signals for, as I just mentioned, this CH is not there, because this is not here, and then NH or OH is not there, because we do not have a broad signal of OH or NH, because if that was there, probably it would have been a carboxylic acid or an amide or things like that. But what we now conclude from here is that this is a ketone which is conjugated with the aromatic ring. That means you have an aromatic ring and then there is a carbonyl group on that. So, that is the nature of the molecule to which the spectrum belongs there. Okay, let us move further. Let us take a few more examples to see that variety of spectra and see that how easy it is to try to get the information regarding the functional group. Okay, look at this spectrum here. Now, this molecule, again one very important signal, 1688 centimeter inverse, because of the carbonyl group, which again is conjugated because the value is close to what we had in the previous case. Then in addition to that, we find that there is a broad signal, which is a very broad signal, starting from about 2400 centimeter inverse to about 3300 centimeter inverse, which is a reasonably broad signal over there. And in addition to that, we have a shoulder around 2500 centimeter inverse, which is very significant. We know that very well. So, this indicates that this could be a COH group which is conjugated to something else. Okay. Now, look at a signal around 3000 centimeter inverse, which has been actually masked by this OH group there, because this broad signal is because of the OH here, and this broad signal actually has masked this signal here because of the aromatic ring. But this is just indication here. We have to look for more information. We find that the more information is somewhere here. We have this signal around 3100 centimeter inverse is accompanied by a signal around 1600 centimeter inverse. So, these two put together, they give a good enough indication that I am dealing with an aromatic molecule. Then of course, we have got something here which tells about the substitution pattern there. So, these three bits of information put together give me an idea that I am dealing with an aromatic molecule, and the likely functionality is that it is a carboxylic acid and it have more likely to be an aromatic carboxylic acid. So, it is a benzene ring or some aromatic ring over there to which this carboxylic acid is linked directly over there. That is how the conjugation will come into picture, because the conjugation with the aromatic ring will bring this carbonyl group at this low frequency here. Okay, let us move further. Look at one more example. Again, objective remains the same, that we need to identify the functional group. Again, tempted to look at this signal at the most intense signal at 1725, which is obviously a carbonyl group. A carbonyl group, it could be an aldehyde or a ketone. If it is an aldehyde or ketone, I look for this region. This gives me two signals here, which are typical of our CH, aldehydic CH over there. So, I am getting my things straightforward right here. So, but in addition to that, we need to get some more information, because we have to, this functional group is obvious from here, but we need to find out the nature of the molecule as well. So, we find that there is no signal above 3000 centimeter inverse, which indicates that is no unsaturation or aromatic ring. That means this basically is going to be a saturated aldehyde. And of course, we do not have signals above 1660 centimeter inverse and 600 centimeter inverse to confirm that there is no unsaturation or aromatic ring, which I just mentioned over there. Because if there was an unsaturation, well, I would have expected a signal somewhere here. In addition to that, I would have expected some signal in this region over here. So, both of them are missing. So, we conclude that this molecule does not have unsaturation or an aromatic ring, and the conclusion comes out to be that it is a molecule to be aliphatic aldehyde there. And this again is a small signal which has come in number of spectra here, which again happens to be an overtone here. The most likely reason for this to becoming this, an overtone to be there. Okay, move further. Look at this molecule. This is a very simple molecule here. Why simple here? Because in this case, if I look around here, I draw a line at 3000 centimeter inverse, nothing is there. That means not aromatic or unsaturation. That means I am dealing with a molecule which is aliphatic in nature, because these signals are because of aliphatic CH stretching there. But in addition to that, I have got a very characteristic signal here, and this signal we know for sure that this signal around 1130 centimeter inverse is nothing but an ether, because this is, that is why we have taken this very simple molecule here, because we know that there are two things are glaringly clear, obvious here. One is it is an ether, secondly it is an aliphatic molecule. So, we can straight away come to a conclusion that this molecule happens to be an aliphatic ether there. These are supplementary information about the aliphatic nature there. This is CH stretching, these are the bending modes over there. So, conclusion is straightforward, I am dealing with a molecule which is aliphatic ether. Okay. Let us move to the next, or maybe the last example here. Again, objective is to find out the functional group. If I look at this, there are two signals, intense ones here, around 3180 and 3350 centimeter inverse. They tell me it is likely to be an NH2. In addition to that, I find, because any IR spectra, something around 1700 centimeter inverse is very, very tempting to look at. So, when we look at that, we find that this is nothing but a carbonyl stretching, likely to be an amide. And this is an obvious thing, we all know so very well now, that is something just below 3000 centimeter inverse happens to be CH stretching there. Okay. So, we have got an NH2 and we got a carbonyl group. An obvious choice comes out to be it to be an amide, likely to be an amide. Then what do we do is, we look at a signal slightly above 3000 centimeter inverse. So, we find that this is fine, this is my NH2. But if we look at just around 3000, below that is aliphatic CH there, but above this nothing is there in between the two signals there. That means it is not an aromatic molecule, and there is no unsaturation, or maybe some unsaturation is there that actually has been masked by this broad signal over there. So, we cannot really be so sure about this, but the most likely observation we can make from here is that this molecule also is likely to be a primary amide there. It is CONH2 as a functional group there. Okay. Now, let us sum up what we have done today. What we have done today is, we briefly reviewed the contents of the previous session, and then thereafter we formulated or devised a strategy for interpreting IR spectra. So, it was one of the suggestions which I shared with you, and on the basis of that strategy, we have used this strategy to interpret a number of IR spectra, and we have seen that how can we use this strategy to work out the functional group for the given molecule to which the spectrum belongs. So, with this we come to the conclusion of this series of lectures here, and I am sure that by now we know fairly well that what are the origins of UV and IR spectra, what are the factors which affect these spectra, and what kind of information can we get from these spectra there. With this we conclude this series of lectures.